There is a particular quality to the light in the Guadalupe Mountains just before the sun completes its descent. It arrives in long, amber columns that fall across the limestone cliffs like something slow and deliberate, as though the light itself has learned patience from the stone it touches. The rock here is old, not old in the way that buildings or forests are old, but old in the way that requires a different relationship with time entirely. These are mountains that remember an ocean. They carry within them the compressed, crystallized memory of a world that no longer exists, a world of warm, shallow water and ancient marine life that flourished and died and slowly became the very ground beneath your feet. Stand here for a moment. Let your eyes move across the ridgeline, across the pale faces of the cliffs, across the dry scrub and the yucca plants reaching upward with quiet determination. The wind, when it arrives, comes in long, unhurried waves. It carries dust and the faint scent of dry earth, and it moves through the mountain passes the way water once moved through these valleys, patiently, without urgency, shaping everything it touches by the simple accumulation of time. This is Guadalupe Mountains National Park in southeastern New Mexico, and on the surface, it tells one story. It tells the story of desert survival, of rock and wind, and the slow persistence of plants that have learned to hold moisture against the dryness of the Chihuahuan desert. It tells the story of open sky and geological drama, of mountains that rose from the earth over millions of years, carrying ancient seafloors toward the sun. It is a beautiful story and a true one, and if you had only ever stood here on the surface and watched the light change across the limestone, you might have felt that you had understood something genuine and complete about this place. But beneath your feet, hidden beneath hundreds of meters of layered stone, there is another story, and that story has barely begun to be told. Before we descend any further, consider subscribing to History Sleepy Time and leaving a like on this video so that we can continue exploring these remarkable places together. We would also love to know where in the world you are watching from tonight. Leave a comment below. Somewhere along a trail in the southern section of Guadalupe Mountains National Park, there is an opening in the earth that, at first glance, asks very little of your attention. It is not dramatic. It does not announce itself. It sits in the rock like a simple crease, a modest downward passage that might easily be passed without a second thought. Early visitors to this area walked past it for years. They felt, perhaps, a slight coolness rising from the opening, a breath of underground air touching the dry warmth of the desert surface. But the significance of that breath was not immediately understood. What lay below this quiet opening was, as scientists would eventually determine, one of the most extraordinary underground environments ever discovered by human beings. Not because of what was hidden there in the way of treasure or mystery or danger, but because of what had been preserved there in complete darkness and extraordinary stillness for an almost incomprehensible span of geological time. The question that this documentary will gently follow, all the way from the surface of the Guadalupe Mountains down into the deepest surveyed chambers of Lechuguilla Cave, is a question that does not demand a quick answer. It is the kind of question that rewards patience. How can a place remain hidden beneath our feet for millions of years and still continue revealing new discoveries today? Let us begin at the beginning. Not at the moment of discovery, but long, long before that, in a time when none of this was mountain or desert or stone, in a time when all of this was sea. The entrance to Lechuguilla Cave does not look like a doorway to one of Earth's most scientifically significant places. That is perhaps the most important thing to understand before anything else. The landscape surrounding it is honest and unpretentious. There are limestone ridges running in long lines across the terrain, worn smooth in some places and fractured in others. There are desert grasses growing in the thin soil between the rocks. There are juniper trees standing at careful distances from one another, their roots reaching deep into the fractured limestone in search of water that collects far below the surface. The air at midday carries heat. The sky on a clear day is an almost architectural blue, precise and enormous, the kind of sky that makes the mountains beneath it seem both very large and very small at the same time. In the late afternoon, when the shadows begin to stretch eastward across the rock, the temperature drops with a noticeable swiftness. The Guadalupe Mountains sit at elevations that allow this. The desert floor gives way to ridgelines above 2,000 meters, and at those heights, the days are warm and the evenings come quickly and carry a chill that the desert below does not share. Hikers on the trails feel this shift. Birds move differently in it. The light itself seems to change not just in color but in texture, becoming something softer and more thoughtful than the bright, flat clarity of noon. And somewhere within this landscape, modest enough to miss if you are not looking carefully, is a small depression in the earth. It sits at the edge of a limestone slope, partially sheltered by rock, partially open to the sky. Early observers noted that air moved through it, not dramatically, not in any way that suggested the vast underground world below, but in a gentle, continuous way that spoke of connected spaces somewhere in the darkness beneath. Cave explorers, who learned to read the subtle language of moving air the way sailors read wind, recognized this as a sign worth investigating. The movement of air through an opening almost always means that the opening connects to something larger, that somewhere below, a network of passages breathes with the slow rhythm of pressure changes, drawing air inward in certain seasons and releasing it in others. This small opening, this unremarkable crease in the limestone of the Guadalupe Mountains, had been known to local cavers for some years before serious scientific interest found it. It was associated with a broader area of cave systems in this corner of New Mexico, a region that includes the famous Carlsbad Caverns just a short distance to the south. Carlsbad had been a place of public wonder since the early 20th century, drawing visitors from across the country to experience its enormous chambers and its famous population of Brazilian free-tailed bats. It was known, celebrated, and partially understood. Lechuguilla was something else entirely. Its entrance, the one that would eventually be cleared to allow passage, dropped only a short distance before meeting the solid floor of a debris-filled pit. For years, this pit had prevented further exploration. The rubble and broken rock at the bottom suggested either the end of the cave or a passage sealed by geological time. But cavers who sat quietly near this entrance reported something that kept drawing them back: the persistent sensation of air moving upward through the debris with a consistency that did not match a dead-end pit. Air does not accumulate, it moves. And if air is moving consistently upward through a pile of cave debris, it is moving from somewhere. That quiet, persistent breath of underground air, cool and faintly mineral-scented, carrying the particular stillness of deep underground spaces, would eventually lead to one of the most significant geological discoveries of the 20th century. But standing here on the surface, with the limestone ridges rising around you and the desert light beginning its long evening fade across the mountains, there is no indication of what waits below. The entrance asks nothing dramatic of you. It simply exists, as it has existed for the entire duration of human presence in this region, offering only a faint coolness and a quiet movement of air to anyone patient enough to notice. This is where daylight stops. And what lies beyond this threshold has spent millions of years becoming something that even now science has not fully described. Perhaps the most extraordinary quality of Lechuguilla Cave is not its depth, though it is among the deepest caves in the United States. It is not its length, though its surveyed passages extend for more than 200 kilometers and continue to grow with each new expedition. It is not even the remarkable formations that fill its chambers, the gypsum chandeliers, the hydromagnesite balloons, the crystal pools, and delicate mineral growths that have no comparison anywhere else on Earth. What makes Lechuguilla extraordinary is its age, its preservation, and the geological story written in its walls. To understand that story, we must first go much further back than the cave itself. We must return to a time before the mountains, before the desert, before the limestone cliffs and the dry air and the yucca plants reaching toward the sky. We must return to the sea. Imagine standing here on this exact ground, in this exact location, in what is now southeastern New Mexico, approximately 250 million years ago. The first thing you would notice is that there is no ground. There is only water. Warm, shallow, sunlit water stretching in every direction, occupying the enormous depression in the Earth's crust that geologists now call the Delaware Basin. This was not an ocean in the modern sense. It was not the deep, cold, open expanse of the Atlantic or the Pacific. It was something more intimate than that, more enclosed, more still. A broad inland sea connected to the larger ocean systems of its time, but partially separated from them, developing its own particular chemistry and its own particular community of life. This was the Permian period. And the Permian world looked nothing like our own. The continents were arranged differently. The single great landmass that geologists call Pangaea was still largely intact, though beginning the slow process of separation that would eventually produce the world we recognize today. The climate was warm. The atmosphere was different. The life that existed was separated from our own by the largest mass extinction in Earth's history, an extinction event that would eventually end the Permian period and reset the trajectory of life on this planet. But in the warm, shallow waters of what would become southeastern New Mexico, none of that had happened yet. In these waters lived enormous communities of marine organisms, corals, sponges, algae, mollusks, and the countless smaller creatures that existed between them and within them and built their lives around them. Together, these organisms constructed something remarkable. They built a reef. Not a reef in the casual sense of the word. A massive, elaborate, ancient reef complex that grew along the edges of the Delaware Basin over millions of years, accumulating layer upon layer of calcium carbonate, the mineral compound that organisms with shells and skeletons leave behind when they die. Generation after generation, these creatures lived and died in the shallow water, and the calcium carbonate remains of their bodies settled slowly downward, compressing, crystallizing, bonding together under the weight of the water and the accumulating material above. The process was geological in its patience. A reef that takes 1,000 years to grow a single meter, and even that estimate varies enormously depending on the conditions. Multiply that by millions of years across an enormous geographic area with the consistent contribution of uncountable billions of marine organisms, and what accumulates is something that will eventually become the Capitan Limestone Formation, one of the most significant and well-preserved ancient reef systems ever identified by geologists. The Capitan Limestone is the rock of the Guadalupe Mountains. It is the pale cliff face you see from the park trails. It is the ridge you walk along, the canyon wall you photograph, the stone beneath your boots. Every surface feature of this landscape is, in geological terms, a fragment of an ancient seafloor, compressed and crystallized and lifted by tectonic forces into the mountain shapes we recognize today. The lifting itself is a story worth pausing over. Somewhere between 20 and 30 million years ago, which in geological terms is relatively recent, the tectonic forces that have always moved and rearranged the surface of the Earth began to affect this region in a new way. The land that would become the Guadalupe Mountains began to rise. It did not rise dramatically or suddenly in any human sense. It rose at the pace that stone rises slowly, measurably only across millions of years, but with enormous consequence. As the limestone formations were lifted upward, the ancient reef that had once sat at the bottom of a Permian sea found itself elevated above the surrounding terrain, exposed to air and weather and the long, patient process of erosion. The sea retreated. The basin dried. The water that had maintained the chemistry of life in the Delaware Basin for millions of years became, eventually, the dry air of the Chihuahuan Desert. What remained was the stone. And stone, as it turns out, is not simply a static thing. It is porous. It is reactive. It is shaped not only by the forces that create it, but by the water and chemistry that move through it over time. The limestone left behind by the Permian Reef was full of fractures, natural pathways created by the stress of tectonic uplift, by the expansion and contraction of rock across seasonal temperature changes, by the slow chemistry of groundwater working its way through calcium carbonate over millions of years. In other limestone landscapes around the world, these fractures and the groundwater that moves through them create cave systems through a process called dissolution. Slightly acidic rainwater, percolating downward through the rock, slowly enlarging fractures into passages into chambers. Chambers into the complex underground networks that geologists call karst systems. Carlsbad Caverns, just a short distance from Lechuguilla, formed partially through this familiar process. Countless other cave systems around the world formed this way, but Lechuguilla Cave did not. Lechuguilla formed through a process so unusual that when geologists first proposed it, the scientific community received the idea with a degree of careful skepticism. The chemistry that created this cave did not come from above, from rainwater and surface processes working their way slowly downward through the limestone. It came from below, and that difference, that single, quiet reversal of direction, produced a cave unlike anything else on Earth. To understand how, we need to follow the water. Not the water falling from the sky, but the water that has spent thousands of years moving slowly through the deep rock below, carrying with it a chemistry older and stranger than ordinary rain. Far beneath the surface of the Guadalupe Mountains, deeper even than the cave passages that explorers have carefully surveyed and mapped, there are pockets and seams of petroleum and natural gas locked within ancient rock formations. These hydrocarbons, the organic remains of ancient life, buried and transformed by geological time and pressure, are not unusual in themselves. The region sits above geological formations that have been associated with oil and gas resources for many decades. But what happens at the boundary between these hydrocarbon deposits and the water-saturated rock above them is something that creates consequences far above, in the limestone of the Capitan Formation. Hydrogen sulfide gas rises. It migrates slowly upward through fractures and faults in the rock, carried by the movement of deep underground fluids, where it encounters water that has collected in the fractured limestone above, the groundwater that moves slowly through the karst system of the Guadalupe Mountains. Something chemically significant occurs. Hydrogen sulfide, when it comes into contact with oxygenated groundwater, undergoes a chemical reaction that produces sulfuric acid. This is not a dramatic moment visible to any observer. It happens in darkness, in stillness, in the slow time of geological processes. But the consequence of that reaction, accumulated across hundreds of thousands of years, is profound. Sulfuric acid is, by nature, a powerful dissolving agent when it comes to limestone. Where ordinary groundwater might take thousands of years to slowly enlarge a fracture into a passage, sulfuric acid works with considerably greater efficiency. It attacks the calcium carbonate of the limestone from within, eating outward from the rising acid front, dissolving the rock and creating voids. First small pockets, then larger chambers, then the interconnected networks of passages and rooms that would eventually become Lechuguilla Cave. This process is called sulfuric acid speleogenesis, and it is one of the least common cave formation processes known to science. Most of the world's caves formed from the top down, water falling from the sky, becoming slightly acidic as it passed through soil and decaying organic matter, then slowly dissolving limestone as it percolated downward through fractures. The chemistry is gentle, the process is gradual, and the result is typically cave passages that follow the natural downward slope of the terrain. sulfuric acid speleogenesis works from the bottom up. The dissolving force arrives from below, rising through the rock along the paths of least resistance, fractures, faults, boundaries between different rock types. The cave that results does not follow the slope of the land above. It follows the chemistry of the rock below. It creates vertical development rather than horizontal, carving deep shafts and tall chambers as the acid front worked its way upward and outward through the limestone. This is why Lechuguilla Cave feels, to those who have carefully explored it, so different from other cave systems. Its passages are not the gentle, sloping tunnels of a typical karst cave. They plunge vertically. They open into enormous chambers far below the surface. They branch and reconnect in ways that reflect the complex chemistry of an acid front moving through fractured rock, rather than the simple logic of water following gravity downhill. And because the cave formed from below, sealed from the surface processes that would normally introduce sediment, organic material, and surface-derived water, it remained extraordinarily clean, extraordinarily preserved, extraordinarily isolated from everything happening on the surface above it. The water that eventually collected in Lechuguilla's deepest reaches was not rainwater that had filtered down from the desert above. It was ancient water, in some cases tens of thousands of years old, carrying a chemical record of the geological conditions that surrounded it. The minerals that precipitated from this water onto the cave walls and floors were not the common calcite formations found in most limestone caves. They were rare compounds, gypsum in extraordinary varieties, magnesium-bearing minerals, sulfate formations, the chemical products of an underground environment shaped entirely by the unusual chemistry of its own creation. The formations that grew inside Lechuguilla Cave grew slowly, in complete darkness, from these unusual mineral-rich waters. They grew over hundreds of thousands of years, completely undisturbed by anything above. No surface flood events sent sediment rushing through the passages. No surface-derived water disrupted the extraordinary delicacy of the mineral growths accumulating in the still, dark chambers below. Lechuguilla Cave was, in a very real sense, sealed from the world above it for most of its geological history, which raises a question that deserves to sit quietly for a moment before we attempt to answer it. If this cave was so completely sealed, if its chemistry and formations and underground environment were so isolated from the surface processes above, what was it that finally revealed its presence to the humans walking on the Guadalupe Mountains? What gave it away? The answer, as it turns out, is air, and a small group of patient people who knew how to listen for it. The name Lechuguilla belongs to a plant, Agave lechuguilla, a spiny, drought-tolerant succulent that grows across the Chihuahuan Desert and the limestone slopes of the Guadalupe Mountains. It is not a large plant. It does not draw particular attention to itself in a landscape full of the various adaptations that desert life requires. It grows in low rosettes of stiff, pointed leaves that radiate outward from a central base, with a single tall flowering stalk that appears once in a plant's lifetime, after which the plant dies and is replaced by its own offspring growing from the roots. The cave that now carries this plant's name was known by a different designation, for much of its early documented history. A small pit in this area had been noted by cavers and park staff as far back as the early to mid-20th century, associated with the broader network of cave features in the region. But the pit itself, the entrance that would eventually become the point of access to the cave, ended in debris. Broken rock filled the bottom of the shaft, and there seemed to be no continuation beyond it. Those who explored caves seriously knew better than to accept that conclusion too quickly. Cave explorers, speleologists, and recreational cavers alike develop, over time, a sensitivity to the signs that a cave system offers when it has more to reveal than its current access suggests. One of the most reliable of these signs is airflow. Moving air in a cave almost always indicates connected space. If air moves consistently through a pile of broken rock at the bottom of a pit, it is moving because it has somewhere to go, because somewhere behind that debris there is passage space with a different pressure, creating the differential that draws air through the obstruction. Throughout the late 1970s and into the 1980s, cavers exploring the Guadalupe Mountains region regularly noted the airflow at the Lechuguilla pit. The flow was not subtle to those who knew what they were feeling. It was consistent, directed, and notably cool, carrying the unmistakable quality of deep underground air. The question was not whether something lay behind the debris. The question was whether that something was accessible and whether the work required to access it was worth pursuing. In 1984, a National Speleological Society expedition received permission from the National Park Service to attempt a dig at the Lechuguilla entrance. The work was unglamorous by any standard, the careful removal of loose rock and debris from a pit that offered no guarantee of reward, conducted by volunteers with a shared conviction that the airflow they were chasing was worth following. The debris was moved bucket by bucket, carefully, with attention to safety and the structural stability of the passage above. The dig continued across multiple visits over several years. Progress was measured in small increments. The passage deepened. The airflow remained consistent, in fact, seemed to strengthen in certain seasons, which experienced cavers interpreted as a sign that the space below was substantial. But the breakthrough remained elusive, and the work required continued patience. In May of 1986, a small team working in the pit found what they had been searching for. Beyond the last obstruction of broken rock, the passage opened. What they encountered was not simply a small chamber or a short extension of the known passage. The passage opened into a vertical shaft that descended far beyond the range of their lights, far beyond any reasonable expectation based on the modest entrance above. The cool air that had been their guide for years was now flowing around them from depths that had not previously been accessible to any human being. The explorers descended carefully, methodically, with the attention and discipline that responsible cave exploration requires. They followed rope systems down through the vertical sections, moved through horizontal passages where the cave leveled briefly, then descended again into deeper shafts. The cave unfolded around them with a pace and a scale that, even to experienced cavers familiar with the Guadalupe region's cave systems, was remarkable. What they had found was not an extension of a known system. It was something entirely new. Something that had been sealed from above for an enormous span of geological time, and that now, in the careful hands of people who understood what they were entering, was revealing itself for the first time in its long history. The National Park Service was immediately informed. Scientists were contacted, and the careful, methodical work of understanding what lay beneath the Guadalupe Mountains began. It is worth pausing here to consider the nature of that beginning. The discovery of Lechuguilla Cave was not a moment of sudden revelation followed by open access. It was the beginning of a carefully managed scientific process, one that recognized, almost from the very first reports to reach park staff and geologists, that what had been found was extraordinarily fragile. The formations visible in even the initial explorations were unlike anything in the nearby Carlsbad caverns. The mineral growths were delicate in a way that suggested they had formed in complete isolation, without the disturbance of flood events, without the introduction of surface sediment, without any of the processes that ordinarily mark a cave system connected to the surface above it. The National Park Service made a decision that would shape everything that followed. Lechuguilla Cave would not be opened to the public. It would be protected as a scientific research site, accessible only to permitted researchers, and the survey teams required to map its passages safely and responsibly. That decision, made in the years following the 1986 breakthrough, is one of the most significant conservation choices in the history of American cave management. It preserved inside Lechuguilla something that cannot be recovered once it is lost, the pristine condition of a geological environment that spent millions of years reaching its current state, undisturbed and complete. And inside that pristine environment, life had found a way to exist. There is a threshold that every living thing on the surface of the earth understands without being taught. It is the threshold between light and darkness. Between the photosynthetic world, the world powered by sunlight, organized around the movement of the sun across the sky, dependent on the energy that arrives from 93 million miles away, and everything else. We are creatures of that sunlit world. Our bodies are tuned to it. Our sleep follows it. Our food, in almost every form we have ever consumed, traces its energy back to sunlight captured by a plant, stored in sugars, passed along through the slow chain of consumption and digestion that connects all surface life to the warmth of the sun above. Descend into Lechuguilla Cave far enough, past the entrance, past the initial shafts, past the passages where faint traces of surface light might still filter dimly through the rock, and you reach a place where that threshold becomes absolute. There is no sunlight here. There has never been sunlight here, not in any meaningful sense, not for the entire geological history of this cave. The darkness in these chambers is not the darkness of a room with the lights off, where your eyes gradually adjust and begin to perceive shapes from ambient light filtering under doors or through windows. It is total darkness. The kind that has no gradation, no partial exception, no distant glow on the horizon. Hold your hand before your face in the deepest chambers of Lechuguilla Cave, and you will not see it. The darkness is as complete and as ancient as the stone itself. And yet in this darkness there is life, not abundant life, not the teeming complexity of a forest floor or a coral reef, but life, specific, adapted, patient life, that has found ways to persist in an environment that seems, from the surface perspective, entirely inhospitable. The first, and perhaps most significant form of life in Lechuguilla Cave, is also the least visible. Microbial communities, bacteria and archaea, the ancient single-celled organisms that represent some of the oldest lineages of life on Earth, exist throughout the cave in thin films on rock surfaces, in pools of standing water, in the thin water films that coat mineral formations. These microbes do not depend on sunlight. They derive their energy from chemical reactions, a process called chemolithotrophy, in which organisms extract energy from the oxidation of inorganic compounds rather than from sunlight or organic food sources. In Lechuguilla Cave, the chemistry of the cave itself provides the energy source. The sulfur compounds that played such a central role in the cave's formation, the hydrogen sulfide and its derivatives, provide chemical energy that certain microbes have evolved to harvest. Other microbes extract energy from the oxidation of iron or manganese compounds in the rock. They live at the very edge of what biochemistry permits, operating with metabolic rates so slow that their timescales bear no resemblance to the rapid generation times of surface microbes living in nutrient-rich environments. These microbes are not simply surviving in an extreme environment. They are participants in a geological process. The thin films they form on cave walls, sometimes visible as faint discolorations or unusual textures on rock surfaces, are actively involved in the dissolution and precipitation of minerals. They participate in the ongoing chemistry of the cave in ways that scientists are still working to understand fully. They are, in a very real sense, part of the cave's living biography. And what makes the microbial communities of Lechuguilla Cave particularly significant to science, particularly worth the careful, restricted access protection the National Park Service has placed around them, is their isolation. Because Lechuguilla was sealed from the surface for such an extraordinary span of geological time, the microbial life within it has had an equally extraordinary span of time to develop without the introduction of surface organisms. What researchers have found in the cave's microbial communities includes organisms with genetic characteristics unlike those of known surface microbes, lineages that may represent evolutionary paths that diverged from surface life long ago, developing in the dark, along the chemical gradients of an underground world. Beyond the microbial level, Lechuguilla Cave hosts a small community of more complex organisms, though the word community perhaps suggests a richness that the reality does not quite support. Cave-adapted arthropods, insects and spiders and crustaceans belonging to lineages that colonized the cave environment over long periods and gradually lost the features that sunlit living requires, have been documented within the cave system. These organisms are typically pale, lacking the pigmentation that surface creatures use to manage ultraviolet radiation. Many have reduced eyes, or eyes that have regressed entirely over generations, in which vision offered no survival advantage. They navigate by touch, by chemical sensing, by the subtle detection of air and water movement in the darkness. The nutrient web that supports these small animals in the cave is thin and remarkable. Without sunlight, there are no plants. Without plants, there is no base of the photosynthetic food chain that supports virtually all surface life. What enters Lechuguilla Cave from the surface is minimal, organic material carried by the slow percolation of water through the limestone above, the occasional organism that falls or wanders into a cave passage and does not return. The microbial communities form the base of what food chain exists. The larger organisms in the cave depend, in various ways, on the chemical energy that the microbes process and make available. This is a closed system, almost entirely self-contained, operating on energy budgets so thin that surface life would recognize them only with difficulty, and yet it functions. It has functioned in various forms for an enormous span of time, adapting, persisting, cycling nutrients through the dark in a rhythm that has nothing to do with the seasons occurring hundreds of meters above. There is something quietly moving about this, if you allow the thought to settle. In complete darkness, in a chemistry created by ancient geological processes, sustained by energy extracted from stone rather than sunlight, life found a way to continue, not loudly, not dramatically, but with the same patient persistence that characterizes everything about Lechuguilla Cave, slowly, in the dark, over more time than we find easy to hold in our minds at once. The question that emerges naturally from this understanding is one that has not escaped the attention of scientists studying Lechuguilla's microbial communities. If life can persist in this kind of environment, completely isolated from sunlight, sustained by chemical energy from rock, surviving on nutrient budgets that seem impossibly thin, then what does that suggest about the possibility of life existing in similar environments elsewhere? That question will return later in this journey. For now, there is a more immediate world to understand, the physical world of the cave itself, the passages and chambers and vertical shafts that must be carefully navigated before any of its deeper secrets can be observed. To follow the explorers who have mapped Lechuguilla, we must understand what the act of moving through this cave actually requires. The first thing that strikes most people who have written about or described the experience of entering Lechuguilla Cave is not the darkness and not the formations. It is the silence. On the surface of the Guadalupe Mountains, even on the quietest days, there is always some sound, wind through the canyon, the movement of a bird somewhere on the ridgeline, the distant settling of heat in the rocks. Sound exists on the surface because the surface is alive with process. Air moving, temperature changing, water evaporating from the soil, insects navigating through the brush. These sounds are often so constant and so familiar that we stop consciously registering them, but they are always there, forming a background presence that we carry with us through every outdoor moment. Descend into Lechuguilla Cave, and that background dissolves. The rock around you absorbs sound differently than open air. The passages carry your own footsteps back to you in ways that make the cave seem simultaneously enormous and intimate. Your breathing becomes audible in a way it never is on the surface. The small sounds of your movement, the soft touch of a boot against limestone, the brief tension of a rope against a mechanical device. The rustle of a jacket sleeve against the cave wall arrive in the silence with a clarity and a presence that changes the way you inhabit your own body. And somewhere, always, there is the sound of water. Not running water, not the sound of a stream or a rushing underground river. In Lechuguilla Cave, the water sounds are smaller and more patient than that. A drop forming slowly on the tip of a stalactite, gathering weight over minutes, falling at last to a pool below with a soft, round sound that moves through the chamber and returns as a quiet echo. Another drop, then silence, then another. The rhythm is nothing like a clock. It has no consistent interval, no mechanical regularity, but it has a quality of patience that is deeply affecting when you have been sitting in the cave's silence long enough to hear it properly. The explorers who have spent weeks at a time in Lechuguilla Cave, sleeping underground in small camps, set up on flat stretches of cave floor, eating from packs, carried down through vertical shafts. Working methodically to survey and map passages that no human eye had ever seen, consistently described the silence and the water sounds as among the most memorable aspects of the experience. Not the formations, which are extraordinary. Not the physical challenge of the vertical descents and the crawling through tight passages, but the silence and the sound of water within it. Exploring Lechuguilla Cave requires specific technical skills and equipment. The cave is not horizontally accessible from its entrance. It requires vertical descent through a series of shafts and drops that begin almost immediately after the entrance passage. Rope systems, descended using mechanical devices that allow controlled lowering and careful ascent, are essential for anyone moving through the cave's upper sections. The initial descent from the entrance to the deeper cave passages involves rope work that requires both technical training and physical stamina. Beyond the initial vertical access, the cave opens into a complex three-dimensional network of passages that move in every direction, horizontally, diagonally, and vertically, both upward and downward. Some passages are large enough to walk through comfortably. Others require crawling or squeezing through narrow gaps in the rock with equipment managed carefully to avoid contact with the formations that line the walls. The cave is not uniformly navigable, and the work of moving through it while also conducting the careful measurements required for surveying is slow, methodical, and demanding. Survey teams in Lechuguilla Cave work with instruments that allow them to measure distances and directions precisely, establishing the position of each new section of passage relative to the sections already mapped. Building the three-dimensional picture of the cave that now extends for more than 200 kilometers of surveyed length. Each survey station is a point in space, its distance from the previous station measured, its direction recorded, its position relative to the cave above and below carefully noted. The cumulative result of thousands of these measurements, taken across dozens of expeditions over nearly 4 decades, is one of the most detailed underground maps in existence. The work is not glamorous in the way that surface exploration stories sometimes become. There are no dramatic races to a destination, no competitive element, no moment of arrival at a clearly defined goal. The surveying of Lechuguilla Cave is a collective scientific effort that advances incrementally, one careful measurement at a time, one new passage at a time, with the consistent understanding that what is being preserved is as important as what is being discovered. Patricia Sizer is one name associated with the long-term survey and conservation effort in Lechuguilla Cave, a caver and researcher who spent years contributing to the careful documentation of the cave's passages. Her experience, like that of others who have worked extensively in the cave, reflects the particular quality of attention that Lechuguilla demands. The cave does not reward hurry. Its formations are too fragile, its passages too complex, its scientific significance too great for anything less than the kind of methodical patience that slow, careful work requires. Underground camps, small platforms of lightweight gear set on flat sections of cave floor, allow survey teams to extend their working time deep in the cave without requiring a full ascent to the surface at the end of each day. Team members sleep in sleeping bags on the cave floor, surrounded by the absolute darkness and the silence broken only by the sound of water. The temperature in Lechuguilla Cave is stable, hovering around 20 degrees Celsius in most sections, a comfortable baseline that does not vary with the seasons above. There are no storms underground, no wind, no rain. The stability of the cave environment means that camping in it, while remote from the surface in every practical sense, carries a particular kind of calm. Days in the cave are structured entirely around the work of exploration and documentation. Teams move into new passages, measure and record their geometry, observe and note formations and features of geological interest, and return to camp. The pace is determined not by ambition or schedule, but by the complexity of the passages and the care required to move through them without damage. A single day of survey work in Lechuguilla Cave might advance the map by a few hundred meters of new passage, which in the context of a cave system that now extends beyond 200 kilometers, represents a small but permanent addition to human understanding of what lies beneath the Guadalupe Mountains. There is a particular quality of humility that develops in people who spend extended time in environments like this one. The cave is indifferent to human presence. Its formations grow and dissolve on timescales that have nothing to do with human lifetimes. Its darkness and silence existed before the first human being ever descended into it, and will continue long after. To work carefully in this environment, to measure and record and preserve without disturbing, is to accept a particular relationship with a place that does not need you, and to find that acceptance genuinely meaningful. The cave has been forming for hundreds of thousands of years. The survey of it began fewer than 40 years ago. Already, what has been mapped is astonishing. And yet, as the survey teams know with quiet certainty, there is considerably more ahead, more passages, more chambers, more formations waiting in the darkness to be reached, and at last, carefully observed. What those formations look like is a question worth answering slowly, because the answer is one of the most extraordinary in the natural history of this planet. Close your eyes for a moment and imagine a chandelier. Not the modest kind, not the simple fixture of a dining room ceiling. Imagine a chandelier of extraordinary scale and delicacy, constructed not from glass or crystal, but from the mineral gypsum, white and translucent, and curved in long, graceful arcs, extending outward and downward from the ceiling of an underground chamber in formations that can reach several meters in length. Imagine the way light would move through such a structure, the way it would scatter and soften, the way each curved mineral fiber would carry the light differently depending on its angle and thickness. Imagine the silence in the chamber that holds this formation, the still air that allowed each mineral fiber to grow undisturbed across thousands of years. This is not imagination. This exists in actual chambers of Lechuguilla Cave, created by geological processes that operated in complete darkness across spans of time that make human architecture seem momentary by comparison. The gypsum chandeliers of Lechuguilla Cave, and chandelier is not a fanciful name. It is the term used by researchers and cavers to describe these formations, are among the most remarkable natural structures ever documented. They form when calcium sulfate-rich water evaporates slowly in underground chambers, leaving behind gypsum crystals that grow outward from surfaces in long, curved formations. The growth is so slow and the cave environment so stable that these formations can achieve their remarkable length and delicacy without ever breaking, because nothing disturbs them. No surface air movement, no flooding, no introduction of external sediment or material. Just the slow, continuous chemistry of mineralized water and the patience of geological time. But the gypsum chandeliers are only one expression of the extraordinary mineralogical variety found within Lechuguilla Cave. There are soda straws, hollow tubes of calcite that grow downward from the ceiling in formations so thin and so fragile that they are among the most delicate natural structures on Earth. A single breath of air in the wrong direction, a slight vibration, any touch at all, these are enough to break a soda straw that has been growing for thousands of years. They hang in clusters from the ceilings of certain chambers, each one a perfect hollow cylinder through which water moves by capillary action, depositing a thin ring of calcite at the bottom as it slowly drips. Where the water drips consistently, the soda straw grows longer. Where conditions change, the growth stops, and the formation becomes a permanent record of the conditions that created it, a tiny geological archive suspended from the cave's ceiling. There are pool fingers and cave pearls, formations that develop in shallow pools of water where mineral precipitation occurs at the water's surface or around small particles. Cave pearls form around a nucleus, a small grain of sand or a fragment of mineral, as calcite precipitation builds up in concentric layers over time, gradually creating a rounded form that resembles, with remarkable accuracy, the pearl formed by an oyster. The Lechuguilla pearls documented by researchers are extraordinarily well formed, reflecting the purity of the cave's water chemistry and the long, undisturbed span of their development. Among the most extraordinary formations documented in Lechuguilla Cave are those composed of hydromagnesite, a magnesium carbonate mineral that forms in specific chemical conditions rarely found in surface or near-surface environments. In certain chambers of the cave, hydromagnesite has precipitated into rounded, balloon-like formations, smooth white mineral shapes that cluster on surfaces in groups, their rounded forms suggesting something organic, something almost biological, though they are entirely the product of slow mineral chemistry. The hydromagnesite balloons of Lechuguilla Cave are scientifically significant not only for their rarity, but for what they reveal about the cave's water chemistry. Magnesium-rich water, percolating slowly through the limestone, carries magnesium carbonate in solution. Where conditions are right, where evaporation and temperature and water chemistry align in specific ways, the hydromagnesite precipitates from solution, building up gradually into these extraordinary rounded forms. Finding them in the abundance and quality observed in Lechuguilla Cave tells geologists something important about the particular underground chemistry of this system, something that could not be learned from any other cave in the world. There are also formations in Lechuguilla Cave that do not fit neatly into any previously established category, unusual mineral growths, whose chemistry and growth mechanism required new research to explain. Anthodites, radiating clusters of aragonite crystals that grow outward in all directions from a central point, resembling something between a sea urchin and a snowflake rendered in white stone, appear in some chambers. Moonmilk, a soft, white, paste-like material made of microcrystalline calcium carbonate that forms on cave walls in specific humidity conditions, covers sections of wall in a way that suggests both geological and possibly microbial processes working together. The diversity of these formations, the sheer variety of mineral types and growth patterns present in a single cave system, reflects the unusual chemistry that the sulfuric acid speleogenesis process introduced into Lechuguilla Cave. Most limestone caves, formed through conventional dissolution by surface-derived water, display a comparatively limited range of formations, predominantly calcite stalactites and stalagmites in various forms. Lechuguilla's more complex origin produced a cave environment with more complex chemistry, and that chemistry produced formations that span a broader mineralogical range than virtually any other cave system on Earth. Researchers studying Lechuguilla Cave formations have used them as archives, records of past conditions that can be read, with appropriate analytical techniques, to reveal information about the climate and hydrology of the region over hundreds of thousands of years. The isotopic composition of the minerals, the layering patterns within formations that grew in multiple stages, the presence or absence of specific trace elements. These contain information that cannot be recovered from the surface environment, where erosion and weathering and biological processes have disturbed and redistributed the geological record. A cave formation that has grown undisturbed for 500,000 years in a sealed underground environment is, in a very real sense, a letter written by the geological past to the scientific future. Lechuguilla Cave is full of such letters. And what makes them so extraordinary, What makes the decision to protect this cave from public access so clearly and completely justified is that each one of these formations exists only once. There is no second copy. The gypsum chandelier in its particular chamber, shaped by the particular chemistry of this particular water, in this particular period of geological time, this exists nowhere else on Earth. Break it, and the thousands of years of its growing are gone in a moment. Disturb the water chemistry of the pool in which a cave pearl has been forming, and the conditions that allowed it to develop may never return. This is the weight of what the National Park Service agreed to protect when it restricted access to Lechuguilla Cave. Not simply a beautiful underground space, but an archive of geological history so fragile and so complete that it required the kind of careful, permanent protection that public access would make impossible. It is worth resting here, in the quiet of these imagined chambers, with the mineral formations growing in the darkness around us, and allowing the question to return. How has a place this extraordinary remained hidden, remained sealed, remained so completely untouched for so long? And what stories, beyond the geological ones, surround the mountains above it? The Guadalupe Mountains have not always been as quiet as they sometimes appear. This landscape has been home to human beings for a very long time. Archaeological evidence suggests that people moved through and lived within this region for at least 13,000 years, perhaps longer, depending on how the archaeological record of the broader Southwest is interpreted. The Guadalupe Mountains represent a significant ecological zone within the larger Chihuahuan desert landscape, an elevated area with greater rainfall than the surrounding lowlands, supporting more diverse plant and animal communities, and therefore more diverse opportunities for the human beings who inhabited this region across millennia. The most extensively documented indigenous presence in the Guadalupe Mountains region in the historical period belongs to the Mescalero Apache, who inhabited this area and the surrounding territories for centuries before Spanish colonial contact in the 16th and 17th centuries. The Mescalero drew upon the resources of the Guadalupe Mountains with great knowledge and sophistication. The Lechuguilla plant itself, for example, was a significant food and fiber source, its heart roasted in earthen ovens for nourishment, its fibers used in the production of cordage and other materials. The mountains were not simply a landscape to pass through but a homeland, a place with specific named features, established roots, seasonal resource sites, and a deep accumulated knowledge of the land's character and offerings. It is important to state clearly what the historical and archaeological record does and does not tell us about the relationship between indigenous peoples of this region and the caves of the Guadalupe Mountains. There is documented use of some cave features in the broader region. Carlsbad Caverns, for example, contains archaeological evidence suggesting human presence in certain accessible areas. But the evidence for any deep exploration of Lechuguilla Cave specifically before the modern period does not exist in the archaeological record, which is consistent with what we know about the cave's physical accessibility. The entrance to Lechuguilla was blocked by debris, and the passages below that entrance were not accessible without the technical equipment and deliberate excavation that the 1980s exploration required. There are stories associated with the caves of this region, stories that belong to local oral traditions and to the accumulated folklore of the communities that have inhabited this landscape across generations. These stories are part of the cultural heritage of the area, and they deserve to be acknowledged with respect. But it is equally important, in a documentary committed to historical accuracy, to say clearly that these stories belong to cultural tradition rather than to documented historical evidence. They are not scientific accounts of what lies within the earth. They are expressions of how people who lived in this landscape understood and related to its features, a type of knowledge that is genuine and worth honoring, while remaining distinct from the geological and scientific record. The broader regional landscape carries stories about the significance of underground spaces, the association of caves with water, with the natural world's capacity to provide and withhold, with the particular atmosphere of underground places that affects all human beings who enter them, regardless of cultural background. These associations are universal. Every culture that has lived near significant cave features has developed some relationship with them, some way of understanding and articulating the particular quality of underground spaces, the darkness, the different air, the sounds and silences that distinguish them from the surface world. What is striking, when you consider the Guadalupe Mountains and the cave beneath them, is how thoroughly the underground world managed to keep its greatest secrets from the human beings moving across the surface above. The largest and most extraordinary chambers of Lechuguilla Cave, the gypsum chandeliers. The hydromagnesite formations, the ancient pools and mineral growths that make this cave unlike anything else on Earth, were completely unknown to any human being of any culture or period until the last decades of the 20th century. The mountains kept their secret not through any supernatural quality, but through simple geology. The entrance was sealed. The cave was deep. The formations within it formed in darkness that had never been interrupted by human light. And the people who lived on the surface above, however intimately they knew the mountains, however carefully they observed the landscape, had no means of knowing what the limestone beneath their feet contained. This is worth a moment of quiet reflection. For thousands of years of human presence in this landscape, the gypsum chandeliers hung undisturbed in their dark chambers. The hydromagnesite balloons slowly accumulated their mineral layers. The cave pearls floated in their pools. The microbial communities continued their ancient chemical work in the darkness. The water dripped with its patient rhythm into pools that no human eye had ever seen, creating ripples that traveled across the pool and died against the far wall, in a silence that had never been interrupted. All of this was happening beneath the feet of the human beings who walked this landscape, hunting, gathering, establishing roots, building shelters, telling stories, living their lives on the surface above, entirely unaware. The cave did not announce itself, it simply continued. And in that continuation, in that millions of years-long patience, it preserved something that the surface world, with all its disturbance and change and biological complexity, could never have kept intact. It preserved a record. And that record, as scientists would eventually discover, contained information of significance far beyond the Guadalupe Mountains. There is a particular kind of scientific patience that underground environments demand. It is not the patience of waiting for a result, the familiar patience of an experiment running in a laboratory, of data accumulating in a database, of a culture growing in a petri dish under controlled conditions. It is something older and quieter than that. It is the patience of learning to read a place on its own terms, in its own time, without imposing the urgency that surface science often carries with it. Lechuguilla Cave has taught this patience to every researcher who has entered it carefully and stayed long enough to begin understanding what they were looking at. From the earliest years following the 1986 breakthrough, scientists recognized that Lechuguilla Cave represented something beyond an unusually beautiful or geologically interesting underground environment. It represented an opportunity that could not be replicated anywhere else on Earth. The chance to study a sealed geological system in a state of preservation that the surface world, with all its constant disturbance and biological activity, makes impossible. The cave was not simply a place to visit and describe. It was, in the most literal sense, a laboratory, one that nature had been quietly preparing for hundreds of thousands of years before any human scientist arrived to begin working in it. The scientific disciplines that have found Lechuguilla Cave relevant to their work span a remarkable range, and the connections between them are one of the most intellectually satisfying aspects of the cave's ongoing study. Geology, most obviously, found in Lechuguilla Cave a record of the Guadalupe Mountains' hydrological and chemical history, stretching back further than surface erosion, and weathering allow the geological record to be preserved above ground. The cave formations, particularly the speleothems, the general term for mineral deposits formed within caves, are among the most carefully preserved geological archives in the American Southwest. Researchers studying the layered growth of these formations have been able to reconstruct aspects of regional climate history, identifying periods of greater and lesser rainfall, shifts in the regional water table, and changes in the chemistry of water percolating through the limestone above. The technique used for this reconstruction is called speleothem paleoclimatology, and it works by analyzing the chemical composition of mineral layers deposited at different times within a cave formation's growth history. Because calcium carbonate and other minerals precipitate from water carrying a chemical signature of the conditions at the time of precipitation, the temperature, the isotopic composition of the water, the concentration of various trace elements, each layer of a speleothem is in a sense a record of the conditions that existed when that layer formed. A formation that has been growing for 500,000 years contains 500,000 years of layered climate information, readable by researchers with appropriate analytical tools. Lechuguilla Cave's speleothems are particularly valuable for this kind of research because of the cave's extraordinary preservation. In a cave that has experienced flooding or significant introduction of surface sediment or repeated disturbance by biological activity, the chemical integrity of the speleothem record may be compromised. Layers dissolved and redeposited, trace element concentrations altered, isotopic signatures mixed across different time periods. Lechuguilla Cave's isolated, stable environment has protected its speleothems from most of these disrupting influences, leaving their chemical records more intact than is typical. The climate information encoded in these formations is not simply of academic interest. Understanding how this region's climate has varied across hundreds of thousands of years, how rainfall patterns have shifted, how the water table has responded to different climate states, how vegetation and hydrology have co-varied across deep time, provides context for understanding the region's future climate trajectory. Every piece of climate archive evidence adds to the larger scientific picture that allows researchers to better understand the relationship between atmospheric conditions and regional environmental response. But the geological and climatic research, substantial as it is, represents only one dimension of what Lechuguilla Cave has offered to science. The microbiology of the cave has proven to be, in the assessment of many researchers who have studied it, among the most scientifically consequential discoveries associated with the cave since its opening in 1986. The microbial communities of Lechuguilla Cave are not simply interesting as biological curiosities. They have direct relevance to some of the most pressing questions in contemporary science. In the 1990s and early 2000s, as the initial surveys of the cave's microbial diversity began to produce results, researchers found organisms with characteristics unlike those of known surface microbes. The genetic sequences of certain cave microbes placed them in evolutionary positions, suggesting long isolation from surface lineages. Divergences that may have begun when the cave's sealing from surface processes cut off the exchange of organisms between the underground and surface environments. Some of these organisms were found to produce chemical compounds, secondary metabolites, molecules created as byproducts of their metabolism that had never been previously described in the scientific literature. Among these compounds were molecules with antibiotic properties. This discovery attracted significant attention from the broader scientific community, and with good reason. The development of antibiotic resistance among pathogenic bacteria has become one of the most serious challenges in contemporary medicine. The search for new antibiotic compounds, molecules that can interfere with bacterial function in ways that resistant organisms have not yet evolved defenses against, has become increasingly urgent as existing antibiotics face diminishing effectiveness against certain pathogens. The antibiotic-producing microbes of Lechuguilla Cave represent a potential source of novel antibiotic compounds, precisely because they have been isolated from surface environments, and their evolutionary development has proceeded along pathways that surface organisms, including the pathogens that existing antibiotics target, have not followed. The chemical weapons that cave microbes have developed for competing with one another in the resource-scarce cave environment may include molecules effective against organisms that have never encountered them, and therefore have no evolved resistance to them. Research into the antibiotic potential of cave microbes is ongoing and appropriately cautious. The path from an interesting laboratory observation to a clinically useful antibiotic is long, complex, and uncertain. But the scientific rationale for pursuing this research is sound, and Lechuguilla Cave is among the most productive environments yet identified for finding microbial lineages with novel biochemistry. A remarkable study published in 2016 by researchers including Hazel Barton, a microbiologist who has spent years studying cave microbial communities, examined bacteria collected from Lechuguilla Cave and found that many of them showed resistance to multiple modern antibiotics, not because they had been exposed to those antibiotics, which is the mechanism by which surface bacteria acquire resistance, but because the biochemical machinery that confers resistance appears to be an ancient feature of these organisms' biology, predating the development of modern antibiotics by an enormous span of time. This finding was scientifically significant because it suggested that antibiotic resistance is not simply a product of modern medical overuse. It is a deeply ancient biological strategy, and understanding its origins in isolated environments like Lechuguilla Cave may help scientists understand and address the broader problem of resistance. The water chemistry of Lechuguilla Cave has also drawn scientific attention, particularly in the context of understanding what kinds of chemical conditions support life in extreme environments. The water in Lechuguilla's deeper sections is ancient. Some of it has been isolated from surface water recharge for tens of thousands of years, and its chemistry reflects this isolation. The dissolved mineral content, the pH, the concentration of sulfur compounds and their derivatives, these create a chemical environment quite unlike the fresh water of surface streams and aquifers, and quite unlike the water in more conventional cave systems. Studying life in this unusual water chemistry, understanding which organisms can survive in it, how they process the available chemical energy, what metabolic strategies they employ, contributes to the broader scientific understanding of what conditions life requires and what conditions it can tolerate. And this broader understanding has implications that extend far beyond the Guadalupe Mountains. In the early 2000s, as the exploration of the solar system began to reveal that liquid water, or at least the conditions that might support liquid water, exists in environments beyond Earth, the scientific community began paying close attention to what extreme environments on our own planet could tell us about the possibility of life elsewhere. The ice-covered oceans of Jupiter's moon Europa, the subsurface briny water that may exist beneath the surface of Mars, the hydrocarbon lakes of Saturn's moon Titan. These environments share certain characteristics with the extreme environments found in isolated cave systems on Earth. Lechuguilla Cave, with its chemolithotrophic microbial communities deriving energy from rock chemistry rather than sunlight, its ancient isolated water chemistry, and its extraordinary degree of isolation from surface processes, has been identified by researchers affiliated with NASA and other space science organizations as a relevant analog environment for thinking about life in these extraterrestrial contexts. If life can sustain itself in complete darkness, in isolation from sunlight, deriving energy from the chemical reactions of rock, as it demonstrably does in Lechuguilla Cave, then the conditions for life may exist in environments that receive no sunlight at all. This is a thought worth holding carefully because it changes the question. For most of human history, the presence of life has been understood as dependent on sunlight. Life exists where the sun reaches. The discovery that chemolithotrophy, life powered by rock chemistry, can sustain complex microbial communities in deep isolation has expanded the conceptual space in which life might be possible. Lechuguilla Cave did not create this scientific insight alone, but it contributed to it in a significant way, providing a well-studied, carefully documented example of a life-sustaining underground environment that operates on principles entirely independent of sunlight. The cave, in other words, is not simply a remarkable geological feature in the American Southwest. It is a data point in one of the most fundamental questions that human science has ever asked. And that, perhaps more than anything else, is why the careful, restricted access approach that the National Park Service has taken to Lechuguilla Cave represents not simply good conservation policy, but good science policy. Every unauthorized visit, every footstep that disturbs a microbial film, every touch that alters the chemistry of a mineral formation surface, every introduction of surface organisms into the sealed cave environment reduces the scientific value of what remains. The cave's value to science is directly proportional to its preservation, and its preservation is directly proportional to the discipline with which human access to it is managed. The researchers who work in Lechuguilla Cave understand this more clearly than anyone. They enter the cave with equipment carefully cleaned to prevent the introduction of surface microbes. They follow designated routes to avoid disturbing formations and microbial communities off the established paths. They remove everything they bring in. They record everything they observe. And they do all of this knowing that the cave they are studying will still be here, still growing, still hosting its communities of microbial life, still accumulating its mineral records of climate and water chemistry long after their particular research questions have been answered and new ones have taken their place. The cave is patient, the science is ongoing, and the questions that remain unanswered are, in many ways, the most interesting ones. More than 200 kilometers of passage have been surveyed in Lechuguilla Cave since the 1986 breakthrough. Let that number sit for a moment. 200 kilometers of underground passage, carefully measured, three-dimensionally mapped, documented in the kind of detail that scientific survey requires. If you were to walk 200 kilometers on the surface, you would cross a significant portion of a small country. You would pass through different landscapes, different weather, different communities of plants and animals. You would experience the full range of what a large geographic area has to offer. All of that distance exists underground, beneath the Guadalupe Mountains, in a cave that from the surface shows nothing more than a modest entrance in a limestone slope. And yet, the survey teams who have devoted years of careful work to mapping Lechuguilla Cave are not working toward a conclusion. They are not approaching the moment when they will have seen everything the cave contains and the map will be complete. The reality is the opposite. Each new section of passage that is surveyed tends to reveal additional passages branching from it, additional vertical drops, additional horizontal extensions, additional chambers that open beyond the boundaries of what has so far been reached. The cave continues. In the deepest sections currently reached by survey teams, Lechuguilla Cave descends to more than 480 meters below the surface. These deepest areas are among the most technically demanding to access, requiring multiple days of travel from the entrance, through vertical sections that demand careful rope management, through passages that require the full range of technical caving skills developed by experienced explorers. The teams that reach these depths are small, well-trained, and methodical. What they find in the deeper sections of the cave is consistent with what the cave has offered at every level: extraordinary formations, unusual mineralogy, evidence of the unusual chemistry that created and continues to shape the cave environment. But the deepest sections also carry something additional. They carry the presence of water, not in the form of dripping stalactites or quiet reflective pools, but in the form of sumps. A sump is a section of cave passage that is completely flooded, where the cave floor meets standing water that fills the passage entirely, with no air space above. Sumps in Lechuguilla Cave are barriers to further exploration using conventional methods. They require cave diving, the application of diving equipment and technique to underwater cave passage, to penetrate, and the logistics of transporting diving equipment to the deepest sections of a cave like Lechuguilla are extraordinary. Some of Lechuguilla's sumps have been explored by cave divers working in conditions of extreme technical difficulty. What they have found beyond these flooded sections suggests that the cave continues, that passages extend beyond the water barriers into additional air-filled sections that have not yet been reached or mapped. The implications of these findings are significant for understanding the full extent of the cave system. Current evidence suggests that Lechuguilla Cave may connect to other cave systems in the region, that the underground network of passages beneath the Guadalupe Mountains is larger and more interconnected than what has so far been mapped. The Guadalupe Mountains are riddled with caves. Carlsbad Caverns, immediately to the south, is the most famous, but the region contains numerous other cave systems, some well documented, some partially explored, some known only as small openings that have not yet been investigated in depth. The geological conditions that created Lechuguilla Cave, the sulfuric acid speleogenesis, the deep hydrocarbon-derived hydrogen sulfide, the fractured Capitan limestone, operated across the entire region, not only beneath the specific spot where the cave's known entrance sits. It is entirely reasonable, from a geological perspective, to expect that additional cave passages exist in this limestone that have not yet been found. How much more lies undiscovered? The honest answer is that no one knows. The survey of Lechuguilla Cave has been proceeding for nearly 4 decades, and in that time, the cave has consistently revealed more passage than was expected at each stage of the survey. There is no geological reason to expect that the currently known 200 kilometers represents the complete extent of the system. There are passages in the cave that end not at solid rock walls, but at breakdown piles of fallen rock that may conceal continuing passage behind them, just as the debris at the entrance concealed the cave itself before the 1986 dig cleared it. There are also sections of the cave that have been identified as geologically promising, areas where the rock structure suggests the likely presence of additional passages, but that have not yet been physically reached because of the logistical challenges of accessing them from the known cave. The cave's three-dimensional complexity means that reaching certain areas requires routes through sections that are difficult or impossible to navigate with current techniques and equipment. Conservation constraints also shape the pace of exploration. The National Park Service's management of Lechuguilla Cave balances the scientific value of continued exploration and survey against the conservation responsibility of protecting what has already been found. Survey expeditions are carefully permitted and managed. The number of people entering the cave at any one time is controlled. The routes that survey teams use are established with attention to minimizing impact on the cave's most sensitive areas. This balance between discovery and preservation, between scientific curiosity and environmental responsibility, is one of the defining characteristics of how Lechuguilla Cave is managed. It is a balance that requires ongoing judgment and recalibration as new sections are found and their conservation significance is assessed. A newly discovered chamber filled with extraordinary formations may prompt a decision to restrict access even to the survey teams who found it, pending a careful assessment of how exploration can proceed without compromising what has been found. The scientists and conservationists who make these decisions are aware that they are managing a resource whose full extent they do not know. They are making choices about a system that continues to surprise them, that has consistently proven larger, more complex, and more scientifically significant than initial assessments suggested. This requires a particular kind of institutional humility, the willingness to revise assumptions, to adjust management approaches as new information arrives, and to accept that the primary obligation is not to the pace of discovery, but to the long-term integrity of what is being discovered. There is something deeply satisfying about a place that continues to be more than expected. In a world where so many landscapes have been fully mapped, fully described, fully understood in their broad outlines, where the age of geographical discovery is commonly described as having ended, Lechuguilla Cave offers the quiet reminder that the Earth still holds genuinely unknown spaces. Not fictional mysteries, not invented secrets, but real, physical, measurable passages that no human being has yet entered, existing beneath a landscape that people have walked across for thousands of years. The unknown in Lechuguilla Cave is not the unknown of conspiracy or legend or unsupported speculation. It is the honest unknown of a geological system too large and too complex to have been fully explored in the years available. It is the unknown that science is designed to address, patiently, methodically, one careful measurement at a time. and every season. In the planned expeditions that the National Park Service permits with careful attention to conservation, the boundary between the known and the unknown moves slightly. One new passage opened one additional chamber, reached one more section of the underground world of the Guadalupe Mountains, becoming, for the first time in its long geological history, a place that human beings have seen. The cave receives these small advances of understanding with the same equanimity that it has maintained throughout its long existence. It continues, as it always has, at its own pace, water dripping, minerals crystallizing, microbes metabolizing in the dark, formations growing. The cave does not need the survey to be complete. It is already complete in every moment, exactly as it is. It is worth asking, plainly and without embellishment, why a sealed cave in southeastern New Mexico should matter to the broader world. Not rhetorically, not as a way of introducing an argument that already knows its conclusion, but genuinely as a question that deserves a careful and thoughtful answer. There are many remarkable places on Earth. There are geological features of extraordinary beauty and scientific interest on every continent, in every ocean, at every elevation from the deep sea floor to the high alpine. Why should this particular place, hidden beneath a desert mountain range and accessible to almost no one, command the attention and the care that it has received? The answer begins with uniqueness, but it does not end there. Lechuguilla Cave is, in the current state of geological knowledge, the only known large cave system formed primarily by sulfuric acid speleogenesis in a condition of such extraordinary preservation. Other caves formed by similar processes exist. Cueva de Villa Luz in Mexico, for example, is a well-studied sulfidic cave system, but none combine the scale of Lechuguilla's passage network with the degree of isolation and preservation that has characterized Lechuguilla since its opening. This combination of size and preservation is not coincidental. The very features that made Lechuguilla Cave inaccessible for so long, the sealed entrance, the depth of the passages, the absence of any large-scale connection to surface water systems, are the same features that protected its formations and its microbial communities from the disturbance that characterizes more accessible cave systems. The mineralogical diversity of Lechuguilla Cave is, by itself, a significant scientific resource. Researchers studying the formation conditions of rare cave minerals, the hydromagnesite, the unusual gypsum varieties, the uncommon sulfate formations, use Lechuguilla as a reference environment. A place where the formation conditions can be studied in situ because they have not been disturbed by the kinds of interventions that most studied cave environments have experienced. The cave is, for mineralogists working on cave-specific mineral systems, an irreplaceable dataset. The climate archive encoded in the cave's speleothems represents scientific value that is not abstract or theoretical. It is directly relevant to contemporary questions about regional climate variability and the relationship between past climate states and current environmental conditions. The American Southwest is a region facing significant questions about water availability, drought frequency, and the long-term sustainability of existing water resource management, under changing climate conditions. Understanding how climate has varied in this region across hundreds of thousands of years, a question that Lechuguilla's speleothem record can help answer, provides context that is genuinely useful for making better decisions about the region's future. Microbiology is perhaps the most immediately consequential scientific area. The discovery of antibiotic-producing microbes in Lechuguilla Cave and the broader finding that cave microbial communities represent ancient evolutionary lineages with novel biochemistry has contributed to a significant shift in how scientists think about the distribution and diversity of microbial life. Before the detailed study of extreme environments like Lechuguilla Cave, the microbial world was understood primarily through the lens of surface and near-surface organisms. The bacteria and archaea familiar from soil, water, and biological research. The discovery of deeply isolated, chemolithotropic microbial communities in caves like Lechuguilla has expanded that understanding in ways that continue to produce scientific insights. For medicine, for astrobiology, for evolutionary biology, and for the fundamental question of where life can exist, the microbial communities of Lechuguilla Cave are genuinely significant. They are not a curiosity, they are a scientific resource. Conservation of Lechuguilla Cave is therefore not simply an aesthetic choice, not simply the decision to protect a beautiful place because beauty deserves protection, though that argument is also valid. It is a scientific choice, made on the basis of clear evidence that the cave's value to science is directly proportional to its preservation, and that its preservation requires the kind of carefully managed, restricted access approach that the National Park Service has maintained since the cave's opening. The model of cave management that Lechuguilla represents, treating an extraordinary natural environment as a scientific research site rather than a public attraction, has influenced thinking about cave conservation more broadly. Other caves around the world with unusual scientific significance have been evaluated against the Lechuguilla precedent, with the recognition that some environments are too fragile and too scientifically valuable for the kind of open public access that other natural features can accommodate. This is a difficult conversation in the context of national parks, whose fundamental mandate includes providing public access to remarkable natural places. There is a genuine tension between the desire to share the wonders of the natural world with as many people as possible, a democratic and generous impulse, and the recognition that some wonders cannot be fully shared without being diminished. Lechuguilla Cave falls clearly on one side of this tension. Its scientific value depends on its preservation, and its preservation requires restrictions on access that most national park visitors will never experience with other park features. But there is another way to think about this tension, one that the documentary format itself embodies in a small way. The experience of Lechuguilla Cave does not require physical presence in the cave to be meaningful. The understanding of what the cave represents, the geological time encoded in its formations, the ancient microbial communities living in its darkness, the climate records preserved in its minerals. The extraordinary range of mineral forms that grew in its sealed chambers over hundreds of thousands of years. This understanding is available to anyone who takes the time to engage with it. And that understanding, in its own way, is more complete and more satisfying than the experience of walking through the cave's passages would be for most visitors. To understand that a place like Lechuguilla Cave exists, to grasp the geological processes that created it, the biological communities that inhabit it, the scientific significance of its preservation, is to have a richer relationship with the natural world. It is to know something true and important about the planet we inhabit, and that knowledge does not require anyone to touch the cave's walls or breathe its air. In that sense, Lechuguilla Cave belongs to everyone, even while it must be protected from nearly everyone. That is not a contradiction. It is in fact one of the more sophisticated things that conservation philosophy has produced, the recognition that some places have more value as preserved scientific archives than as visited landscapes, and that protecting them in that capacity is itself a form of making them available to knowledge, available to science, available to the future. Lechuguilla Cave is not closed to the world, it is open to understanding. And understanding, in the end, is what the cave has always been quietly offering to the geological record, to the scientific community, and now, in a different form, to anyone who takes the time to listen. There is a moment, in the experience of anyone who has spent extended time deep within a cave, when the return journey begins to change the quality of attention. It is not a dramatic change. It does not arrive with any announcement. But somewhere in the careful, methodical process of ascending back through the passages and vertical shafts that brought you down, coiling ropes, managing equipment, moving with the same deliberate attention to the formations around you that the descent required, something in your awareness begins to shift. The weight of the underground world, so complete and so absorbing during the descent, begins to lighten almost imperceptibly. Not because the cave becomes less interesting or less present, but because some part of the mind that has been entirely occupied with the world below begins to reach, very gently, toward the world above. The ascent through Lechuguilla Cave is long. The passages that must be reversed are the same ones navigated downward, but they present themselves differently on the return. The vertical shafts that required lowering now require climbing the narrow sections that were entered head first, must be exited feet first. The orientation of the cave relative to the body is entirely reversed. It is, in a practical sense, a different journey through the same space. And somewhere in that journey, as the survey teams and researchers who have spent days underground will tell you, the air begins to change. It is subtle at first, too subtle to name with certainty. A slight shift in the quality of the darkness, perhaps, or a very faint alteration in the stillness of the air that could be imagination, or could be the first distant breath of surface wind finding its way down through the upper passages. Then, gradually, undeniably, the air does change. The deep cave air, stable, cool, mineral-scented, carrying the particular stillness of spaces that have never known wind, begins to mix with something less perfectly still. Something that has traveled, even if only a short distance, from the world above. By the time the entrance passage comes into view, and the small opening in the limestone that started this entire journey is visible above, a rectangle of light that seems, after days in the cave's absolute darkness, almost impossibly bright, the transition is nearly complete. Step through the entrance. Stand on the limestone slope in the open air of the Guadalupe Mountains and feel, in the simplest and most complete way, what it means to return. This documentary has been a journey of a particular kind, one that moved not through adventure or danger or dramatic discovery, but through time and chemistry, and the patient accumulation of geological processes that operated in darkness for hundreds of thousands of years before any human being arrived to observe them. It has been a journey through the biography of an underground world, a world created by an ancient sea, shaped by sulfuric acid rising from deep geological formations, sealed from the surface by the simple geology of a debris-filled pit, and preserved in extraordinary condition for long enough to become one of the most scientifically significant natural environments ever discovered. The question that has accompanied this entire journey: how can a place remain hidden beneath our feet for millions of years and still continue revealing new discoveries today, deserves, now that we have traveled together through all that the cave contains, a quiet and honest answer. The answer is not a single thing. It is several things layered together the way the limestone itself is layered, each one resting on what came before. Lechuguilla Cave remained hidden because its entrance was sealed by the accumulated debris of geological time, by the broken rock that fills the spaces near cave openings as limestone slowly weathers and collapses over thousands of years. This is simply what happens. Caves seal themselves, partially or completely, through processes that require no intention and follow no plan. They are sealed by the same geological forces that created them: the movement of rock, the accumulation of material, the slow adjustment of underground spaces to the pressures of the world above. It remained hidden because the geology of its formation, the bottom-up chemistry of sulfuric acid speleogenesis, created a cave that did not connect to the surface in the ways that most cave systems connect. Most limestone caves have openings not only at their entrances, but throughout their systems, points where surface water enters, where surface air moves freely in and out, where the boundary between underground and surface is porous and continuous. Lechuguilla Cave had very few such connections. Its sealed character was a direct consequence of the unusual chemistry that created it, and it continued revealing new discoveries, continues, in the present tense, to this day, because of the scale and complexity of what was sealed inside. 200 kilometers of passage is not a fixed number. It is the current measurement of a survey that is ongoing, advancing with each new expedition permitted by the National Park Service, extending the human understanding of what lies beneath the Guadalupe Mountains one careful measurement at a time. The cave is larger than what has been mapped. The passages continue beyond the current survey boundary. The sumps conceal additional sections that cave divers have not yet fully penetrated. The breakdown piles that end certain passages may conceal additional chambers behind them. The cave continues to exist, fully and completely, in the sections that no human being has yet reached. The formations in those sections are growing at this moment, one slow mineral layer at a time, in perfect darkness, in the same patient rhythm that has characterized the cave's entire geological history. The microbial communities in those unreached sections are metabolizing their ancient chemical energy, living their almost incomprehensibly slow lives in the dark, indifferent to whether or not the survey teams will reach them in the next decade or the next century. The cave does not need to be discovered to exist. This is perhaps the most quietly profound thing that Lechuguilla Cave offers to anyone who takes the time to think about it carefully. Human discovery is not what gives a place significance. The gypsum chandeliers were extraordinary before the first explorer's light fell across them. The hydromagnesite balloons were accumulating their mineral layers when no eye had ever seen them, and none would for thousands of years to come. The ancient water in the deepest pools carried its chemical record of geological history long before any scientist came to read it. The cave was always there. The significance was always there. The discovery simply allowed human beings to begin understanding what had been there all along. There is something in that thought that extends beyond caves and geology, if you allow it to. The natural world is full of processes and structures and communities of life that exist without reference to human awareness of them. Geological time does not pause for human attention. The chemistry of minerals precipitating from ancient water does not require an audience. The slow metabolism of cave microbes in the dark does not depend on scientific interest for its continuation. We are visitors to an Earth that was already extraordinary before we arrived, and will continue to be extraordinary long after we are gone. Lechuguilla Cave makes this truth unusually tangible. You can stand at the entrance, at this modest opening in the limestone of the Guadalupe Mountains, with the desert air around you and the mountain light shifting across the rock, and know with complete certainty that below your feet, right now, the cave is continuing. The water is dripping, the crystals are growing, the microbes are metabolizing. The silence is being maintained by the stone itself, as it has been maintained for hundreds of thousands of years, patient and complete, and entirely indifferent to whether or not anyone is listening. The geological processes that created Lechuguilla Cave operated across a timeframe that makes human history seem like a brief afterthought. The Permian Sea that deposited the limestone of the Capitan Formation existed 250 million years ago. The tectonic forces that lifted the Guadalupe Mountains from that ancient seafloor began their work tens of millions of years ago. The hydrogen sulfide that rose through the deep rock and created sulfuric acid at the water table, slowly dissolving the limestone into the cave system we now know. That process operated across hundreds of thousands of years before any human being walked the surface above. Against this timescale, the 38 years since the 1986 breakthrough represent a single, barely perceptible moment. The human history of Lechuguilla Cave, the digs, the expeditions, the surveys, the scientific studies, the conservation decisions, the careful permitted research. All of it together covers less time than the cave spends growing a single layer of mineral deposit in one of its deeper chambers. We are very new here, and yet, in the brief time that human attention has been directed at this cave, we have learned things of genuine consequence. We have learned how sulfuric acid speleogenesis creates underground environments qualitatively different from those formed by conventional karst processes. We have learned that microbial life can exist in conditions so extreme and so isolated that they share more with hypothetical extraterrestrial environments than with the surface life we are familiar with. We have learned that cave speleothems are climate archives of extraordinary precision, preserving records of regional conditions across timescales that surface environments cannot match. We have learned that rare mineral formations, growing in sealed underground conditions over hundreds of thousands of years, can achieve forms and compositions that have no parallel anywhere else on Earth. And we have learned, perhaps most importantly, that knowing when not to enter a place is itself a form of understanding. The decision to protect Lechuguilla Cave as a scientific research site rather than a public attraction was not made without difficulty. The competing pressures, the desire to share a remarkable natural wonder, the logistical challenges of restricting access to a national park feature, the advocacy of various interests who would have preferred different management approaches, were real. The National Park Service's decision to prioritize scientific preservation over public access was made on the basis of the cave's extraordinary significance and fragility, and it has been vindicated many times over by the scientific discoveries that the cave's preservation has made possible. The gypsum chandelier that hangs undisturbed in its dark chamber, undisturbed because no public foot traffic has brought vibration or humidity or organic material to its vicinity, is still there. It will still be there tomorrow and next year and in a century. The conditions that allowed it to grow will persist. The formation itself will continue if the cave's water chemistry remains stable to add infinitesimally thin new layers to its mineral structure, building on the foundation of the thousands of years of growth that came before. The microbial film on the cave wall, protected from contamination by the careful sterilization protocols that permitted researchers follow, continues its ancient metabolic work, producing molecules that may one day provide insights into antibiotic chemistry or evolutionary biology that cannot yet be anticipated. The climate archive in the speleothem, undisturbed by the groundwater disruption that unmanaged cave visitation would inevitably introduce, remains intact, available to future researchers with analytical techniques not yet developed, asking scientific questions not yet formulated. Lechuguilla Cave is, in this sense, a gift to the future. Not a gift of access, few people will ever enter it, but a gift of knowledge, of the knowledge that exists within it, and that the careful protection of the cave makes available to the scientific inquiry of every future generation that chooses to ask questions of it. This is a form of generosity that requires patience. It requires the willingness to forgo the immediate satisfaction of wide access in favor of the long-term integrity of what is being preserved. It requires trust that the scientific value of the cave is real, that future generations will want to study it, that the questions they will ask of it will be worth the careful preservation that makes those questions answerable. Given what the cave has already offered to science in fewer than 4 decades of careful study, this trust seems well placed. The survey will continue. New passages will be found and carefully mapped. The microbial communities will be studied with increasingly sophisticated techniques as analytical chemistry and genomic sequencing continue to advance. The speleothems will be sampled with methods that extract maximum information while removing minimum material. The cave will, with patient scientific attention and careful conservation management, continue to give. And beyond the reach of the survey, in the passages that the current expedition boundaries have not yet touched, in the sections concealed behind sumps and breakdown piles, in the chambers that the cave's geometry has so far prevented from being reached, the formations will continue to grow. The water will continue to drip. The minerals will continue to precipitate from the ancient water films that coat the cave walls. The microbes will continue their slow, dark, essential work. All of this will happen without any audience. All of this will happen whether or not the next permitted expedition finds a way through the next sump, whether or not the next survey team locates the breakdown pile that conceals the next major chamber, whether or not the next researcher's samples yield the antibiotic compound or the climate data or the evolutionary insight that advances the next stage of understanding. The cave is complete in itself, at every moment, exactly as it is. Stand now at the entrance. The limestone slope stretches away before you in the long light of late afternoon. The Guadalupe Mountains rise to the east and south, their pale rock faces catching the last warm angle of the sun, their ridgelines defining the edge of the enormous sky above. The desert air is dry and carries the faint scent of the scrub plants growing in the thin soil between the rocks. A bird moves somewhere in the juniper trees nearby, a brief sound, then silence. Below your feet, the cave continues. Not as a mystery waiting to be solved, but as a place continuing to be exactly what it has always been. A geological archive of extraordinary completeness, a biological environment of unusual significance, a mineral record of conditions that existed before any human being was alive to observe them. And a reminder that the earth we walk on is older and more complex than any single lifetime, allows us to fully comprehend. The question that opened this journey, how can a place remain hidden beneath our feet for millions of years and still continue revealing new discoveries today, has been answered not in a single moment, but across the entire length of the descent. The cave remained hidden because of the simple, unhurried logic of geology, the sealed entrance, the unusual chemistry, the absence of any surface connection that would have announced its presence. It continues to reveal new discoveries because it is genuinely larger than what has been explored, because its passages extend beyond the current survey boundary, because its microbial communities contain biochemistry not yet fully characterized, because its speleothems encode information that future analytical techniques will be able to read in ways current methods cannot. But there is also a quieter answer, embedded within the longer one. The cave continues to reveal new discoveries because each generation of scientists brings new questions to it. The cave itself does not change significantly from year to year. It operates on geological time, not human time. What changes is the quality and direction of human curiosity applied to it. The researchers of the 1980s and 1990s asked geological questions. How was this cave formed? What does its mineralogy tell us about its origin? How does its formation compare to other cave systems? The researchers of the 2000s and 2010s asked biological questions. What lives in this cave? Where did it come from? What can its biochemistry tell us about evolution and medicine? The researchers of coming decades will ask questions we cannot yet anticipate, using tools not yet developed, finding answers in features of the cave that current science does not yet have the conceptual framework to recognize. A place as complex and as well preserved as Lechuguilla Cave is not fully understood by any single generation of researchers. It is understood incrementally across the accumulated curiosity of many generations, each one adding something to the knowledge that the one before it established. This is how science works at its best, not as a race to a final answer, but as a slow, collaborative, multi-generational conversation with the natural world. Lechuguilla Cave is one of the most extraordinary participants in that conversation that the natural world has yet offered. The light is changing now. The amber columns that fell across the limestone cliffs at the beginning of this journey are longer and lower, stretching across the desert floor in the particular way that late afternoon light behaves in these mountains, warm and unhurried and beautifully patient. As though the light itself has spent enough time in this landscape to have learned something from it. The cave will not change overnight. The gypsum chandelier will not grow a measurable fraction of a millimeter before morning. The hydromagnesite balloons will look exactly as they looked this afternoon, and as they looked a decade ago, and as they will look a decade from now. The ancient water in the deepest pools will carry the same chemical signature it carried this morning. The same record of geological conditions, tens of thousands of years old, encoded in mineral ratios, too subtle for any eye to detect. Readable only by instruments and techniques developed specifically to ask questions of deep time. The cave is, at this moment, continuing to become what it has always been becoming. And we standing here on the warm limestone surface, with the desert mountains around us and the open sky above, are the briefest of visitors to a place that was here long before us and will continue long after. There is nothing frightening in that thought. There is only the quiet pleasure of recognizing something true about the scale of the world we inhabit. The Guadalupe Mountains are made of an ancient sea. The cave beneath them was carved by chemistry rising from deep geological time. The formations inside it grew in darkness for hundreds of thousands of years before any human light fell across them. The microbes living in its depths trace their lineages back to some of the oldest biological strategies on Earth. We arrived recently. We have been careful. We have been curious. And what we have found has exceeded every expectation that the modest entrance in the limestone slope would have justified. That is enough to carry back into the daylight. That is enough to hold quietly as the evening settles across the Guadalupe Mountains, and the stars begin to appear in the enormous sky above and somewhere far below, in the stillness and the dark, in the ancient and patient chemistry of stone and water. The cave continues its long, unhurried work. Long after we return to the warmth of the surface, quiet drops of water will continue shaping unseen chambers beneath the Guadalupe Mountains, patiently building tomorrow's discoveries in a darkness that has never needed an audience and never will. The cave is still there. It is still coming. And that is, perhaps, the most restful thought of all. Thank you for spending this evening beneath the Guadalupe Mountains. If the quiet landscapes of our natural world, the hidden places, the ancient formations, the patient processes of geological time, help you find stillness at the end of a long day, history's sleepy time will continue to explore them with you. Subscribe to the channel so that our next journey finds you wherever you are resting tonight. Leave a like if this documentary kept you company in the dark. And wherever in the world you are watching from, whether the desert is close or very far away, thank you for your curiosity and for the patience to follow it all the way to the bottom. Sleep well.